Alright, hey, welcome back, class. Here again. This time we're going to be talking about bounded integration, the concept of bounded integration and the applications, the computations involved, and kind of what all of this means. Right. Now, so a couple of videos ago, when I kind of introduced the idea of integrals and antiderivatives, and our kind of like, what do areas have to do with calculus video, I talked about this kind of bounded integral, in which we have sort of, we have numbers here. These could be any real numbers for now, right, that are essentially at the end of our integration process. We're going to have one more step, and in that step, we're just going to plug in some numbers, right? So, as a little bit of recap, we talked about bounded integrals in the last video, and how we could take integral of a function such as 3x squared dx. We could take this integral, and it ends up being, I chose this so it'd be convenient, x cubed plus c. And now, and as a lot of you will grow to realize, plus c kind of gets annoying after a while. A lot of times you'll forget about it. Checking that initial condition can sometimes be pretty infuriating, but don't worry, all that goes away with bounded integration. Now, a lot of times, and especially if you are using calculus as a tool for application in something like engineering, chemistry, physics, right, you're going to be dealing with a lot of bounded integrals. Unbounded integrals are mainly to help us understand the idea of what an antiderivative is, right? But I also really like bounded integrals as a way to kind of conceptualize this whole like backwards derivative process. Let me show you what I mean, right? I'm going to take that same function, 3x squared dx, because it's a nice kind of easy function, right? We're going to compute the integral the same way as we always do. We're going to use our inverse power rule here. This is going to end up being x cubed, right? There's no plus c in bounded integration. We'll see why here in a second. Now, there's a quick notational thing. So in the next step of our process, like I kind of alluded to earlier, we're going to be plugging in these bounds a and b. And how we notate this is we say we're going to be plugging in bounds a and b simply by writing brackets around our function, and writing our upper bound at the upper corner of the bracket and our lower bound at the lower corner of the bracket. Now, what this means is we are going to take x cubed and we're going to plug in these bounds, but the order in which we plug them in and kind of operations are very important. Now, this is important. This is going to be a very huge concept for the rest of your life in calculus and math. This kind of output of a bounded integral will be equal to b cubed minus a cubed, right? And now the general formula of this is you're going to get, you're going to plug in your upper bound first to whatever you've outputted with your integral, and then you're going to plug in your lower bound. You're going to subtract the two. You're going to subtract the lower bound from the upper bound, right? And now this idea of subtracting the lower bound from the upper bound leads us to the important concept of bounded integrals, right? And I'll kind of draw this because I think it's very important, right? I'm going to draw the typical math teacher function. It's going to look something like this, right? Let's say we have two endpoints. One is right here, and one is right here. This is going to be this is going to be a function f, right? Now, if we were to take the integral of this function with bounds, this is a, and this is b, right? Meaning this is f of a, and this is f of b. If we were to take an integral over those bounds, we would get an area, right? Bounded integrals are going to compute a direct value for this area, right? And now, this area actually has a special meaning. A couple videos ago, I talked about integrals as ways of computing accumulations of change, which happen to be opposite of slopes, which I'll show you why here. Kind of with my limited space, I'm going to draw a smaller function. This function is going to look probably something like this. Maybe it's going to represent the derivative of this function f is going to be this function. I'm going to call it g, right? And this is going to again be the x-axis. Now, this area here, the area. So saying that g is the derivative of f means that f would be the antiderivative of g. Now, hear me out. if we were to take the integral of this function, g, on bounds a to b, right, we would get an area on this function. And now, kind of ignoring this area up here, the area on the antiderivative will be, or sorry, my bad. Yes, the area on the antiderivative of a function will be equal to the change. Well, hang on, sorry, I said that wrong again. The area of your original function will be equal to the change of your antiderivative. And that's where we get that kind of whole subtraction thing. And now, kind of because I messed up my speech there, I'll come up with another example for you all, and then try to better explain it. We have a function, let's say, just x squared, right? X squared. We're going to take the integral of this function at x squared. We know f of x is equal to x squared. Cool. Now, I'm going to say g of x, which is going to be the antiderivative of f of x, is going to be equal to x cubed over 3. And I'm not going to include plus c because we're dealing with bounded integrals. Now, let's do this over the interval 0 to 3. 0 to 3. Well, actually, let's do 0 to 2. 0 to 2. Right. Now, we're going to compute this integral. I forgot to write dx. Perfect. Cool. This integral is going to be equal to, again, x cubed over 3, just using our power rule. And we're going to have bounds from 0 to 2. Right. Now, plugging this in, I'm going to do this work down here. It's going to be equal to 2 cubed over 3 minus 0 cubed over 3, which is going to be equal to, okay, 2 cubed is 8. 8 thirds minus 0 is just equal to 8 thirds. Right. Now, but recognize that this x cubed over 3 here is g of x, which I have defined as the antiderivative of f of x. Now, what this is showing is that this area computation, because this integral calculates an area, this number here, 8 thirds, is the area under the curve bounded by x equals 0 and x equals 2. And on x squared, that would look something like this. If this is, oh, that was a horrible graph of x squared. All right. It looks something like this. That's not much better, but this is x equals 0, and let's say this is x equals 2. We just calculated this area, and this area happens to be 8 thirds, right? What this is saying is this integral, the area of this function bounded by 0 and 2 is equal to the change, the final minus initial, the change in the function value of the antiderivative from 0 to 2, which I think is a very, very interesting concept, because that's what this is showing, is that our antiderivatives, the area is going to be opposite to a derivative, a slope, right? If we want to find a change in a function, we can look at an accumulation of area. And if we want to find an accumulation of area of a function, we can look at that function's antiderivative's change, right? Much how if we want to find a slope of a function, we could take a derivative. Now, if we have a derivative function and we take an integral of that derivative, we're going to get our original function, right? Because derivatives and integrals are inverse operators, and we'll talk about that more later when we deal with the fundamental theorem of calculus. But what that's saying is that if you want to find you know exactly how your function is changing, you can just calculate the area of that derivative. Now, if you think of a function as kind of made up of infinitely many little slopes as whatever they may be, if you were to add up all of those slopes and like kind of take their area, that's how your function changes, right? So areas are a really good way to show how our functions change. Now, derivatives are a good way to show how our functions change instantaneously over some time or some distance or whatever you're looking at, but integrals are really, really good at showing us just how something changes, right? Now, again, like I said, bounded integrals have a very large application in fields like, I mainly think of like engineering, physics, kind of like that. Remember, calculus was kind of invented to help Isaac Newton with physics, so the two really go hand in hand. if you couldn't tell by now, I'm a huge physics guy. So, right. With this, that's kind of like the big introduction to bounded integrals that I have. I want to introduce some new kind of notation methods, because a lot of you might not want to write those like big brackets with like b and a and stuff like that. That kind of gets annoying. Now, let's say we have integral of 3x squared again. I love this function because it's so easy to integrate. And it gets us a higher order polynomial, right? This is going to be equal to x cubed. And if we have bounds a and b, right, we can write this as, with our little brackets, from a to b, right? Or we can write this as x cubed with just one bracket. This is very acceptable, very commonly used. Or what I see most often as I continue my education is just a giant line, a to b. Remember way back to derivatives when I said you can use this kind of like vertical line to signify that you're plugging in something to a derivative? You do the same thing with integrals. Just make sure that your upper bound is going on top and your lower bound is going on bottom, always. Right. Now, with that, I guess we could kind of go through some more examples. The examples I used were pretty limited. I mean, we only had one-term polynomials, right? We could do the exact same thing with our other integration methods that we kind of talked about last video. We can do like the integral of the sum. We could do the integral of the difference of all that. So now I'm going to choose still a relatively easy function. Let's go the integral from 0 to 1. This is still pretty simple. Let's go with 3x to the 4th power minus 4x cubed minus 2x squared plus 7 dx. Now I just made this up. We're going to do this integral together. Here it is on my board. Right. This is going to be equal to, and I'll kind of preemptively draw out my brackets because I know this is a bounded integral. I'm not going to have plus c because, okay, and I didn't really explain why we don't have a plus c. We're not computing an antiderivative much so to find what that antiderivative is. We are computing an antiderivative such that we can calculate its change, such that we can calculate our original function's area. So the purpose of a bounded integral is to calculate an area by directly plugging things into the antiderivative, and the purpose of an unbounded integral is to just find that antiderivative, right? And so we're kind of skipping that whole like, oh, what is the antiderivative step? Because it shows up inside of our brackets here. We found it, we're just plugging some stuff in. We don't need to worry about any initial condition or anything, because, I mean, if we have our original function, I mean, we're just finding that area. There's no initial condition associated with that area. I hope that made sense. Kind of a little rushed and weird. All right, let's do this integral. We're going to add 1 to the power. So this is going to be x to the 5th, 3x to the 5th, and then divide by the new power. So it's going to be 3/5 x to the 5th, and then minus, I chose this one because it's just going to be x to the 4th. We're going to add 1 to the power, divide by the power. It's going to end up being negative x to the 4th, and then minus, I'm going to go through this one quickly, 2/3 x cubed, and then plus 7x. And then that's going to be from 0 to 1, right? And so that's my integral computation. And now we're going to evaluate this integral by plugging in the bounds. And now, when we subtract 0 from everything, since everything has an x term in it, well, that's going to cancel out. I chose 0 because it'd be nice and easy. And a lot of times in real life, your lower bound often is going to be 0, because a lot of times you're going to be looking about how something changes from rest, like, or you know, maybe your time interval starts at 0. A lot of times we use integrals with time, and oftentimes we want time to start at time equals 0, and then we like use a stopwatch to record how much time has passed. So this is going to be 3/5, times 1 to the 5th power, which is just 1, and then minus 1 minus 2/3 plus 7. Okay, this isn't the nicest function to simplify. I can tell you that that's equal to 3/5 plus 6 minus 2/3. Oh boy, how do we want to do this one? You know. A lot of math teachers really don't care if you simplify your answer. I'm just going to leave my answer as that. That's going to be my area. I know that this is going to be some number, right? It's going to be some positive number, and I chose this because I think it leads in it leads in perfectly to kind of our conclusion of the day. We're going to be talking about we're going to be talking about like what bounds can do to the output of a variable, because if you noticed, or I mean, if you think about it, with the way these functions and bounds work, you could get a negative number, right? And that negative number confirms the existence of a negative area, right? And so what does a negative area mean, right? Well, a negative area would be, I guess, synonymous to like a negative slope. Like, what happens if your derivative is negative? Oh, well, your slope is negative. Now, what happens if your area is negative? Oh, that just means your antiderivative decreased, right? That means that your upper bound calculation is going to be lower, or yes, more negative than your lower bound calculation, right? So we're going to introduce this concept of negative areas, and I'm going to draw this kind of this axis here. It's going to be weird. It's going to be like quadrants 1 and quadrants 4. Let's take a function, say sine of x. That's going to look something like this. That was a really bad sine of x function. You get the idea. Actually, I'm going to wipe this from the face of the earth. You never saw that. Cool. So we're going to talk more about trig functions later. We're not going to actually do some computations here, but what's important is that areas above the x-axis I will define as positive. Now, areas below the x-axis are going to be negative. So just by visually looking at a function, you're going to be able to tell that when that function's below the x-axis, you are accumulating negative area. Your antiderivative is going to be decreasing, right? Because if you were to think about it, the antiderivative of this function is going to be some other function. If we were to take the derivative of that function, we would get this. And so this is a derivative of our antiderivative, and so because this is negative, that means our antiderivative is going to be decreasing, right? And so that kind of derivative, integral, increasing, decreasing logic stays with us. We learned about that kind of a while ago, about what it means for our integral, or for our derivative to be positive or negative, what it means for our function to be increasing or decreasing. That logic stays here, right? So negative areas do exist. I would like to warn you about that. Be aware of that existence. Right, and now, so let's go back to our kind of basic A, B example. Let's take integral of just dx from A to B. Now, we know this is going to be x from some A to B. Okay, now, but what were to happen if I were to just, for some reason, flip these bounds? What is the integral from B to A of dx? And I'd like to make this kind of condition here, that b is greater than a, right? B is going to be further along the x-axis, or whatever axis you're thinking about, than a, right? And so now we're integrating backwards. If you were to think about, we have a function and we're integrating from a to b, we're really accumulating an area. We're going from left to right here. If I were to draw this, oh, you can't really see that. Yeah, I'm going to start here at the left, and I'm going to just draw over to the right. I'm accumulating area, right? And now, this is kind of a more abstract concept, and like I talked about negative areas can kind of exist above the x-axis because of this. Because what ends up happening is if you flip the bounds, and this is an important identity, you actually are just multiplying your function by -1. So this is an important one here. The integral from b to a of dx is going to be equal to -1 times the integral from a to b. So all that happens when you flip your bounds, you put the top one on the bottom and the bottom one on the top, is you multiply your result by -1. And now, visually, you can think about this as, okay, we have some function, and instead of moving my pen from left to right and accumulating area, I could think of moving my pen from right to left, and I'm actually kind of like going backwards, and so we're losing area, right? And if you were to think about it now, your antiderivative, you know how our area of our function is directly given by how our antiderivative changes. If we were to go from here to there, our antiderivative is going to change like that, right? So our area is going to kind of increase. But if we were to go from here to here, our antiderivative is going to change this way, and so our area is going to kind of dwindle, right? And so this is a more important identity, less so as like a concept to know, or more so as a concept to know than to like have mastered. It's particularly a useful tool if you kind of want to just get a negative out of there, but you got to be careful because when you evaluate this backwards integral, you are going to have to plug in your bounds properly. Your a is now going to be your upper bound, so you're going to plug in that one first, and so it'd be a minus b at that point, right? So, and again, flipping your bounds is more so a tool that will very occasionally come in handy, right? It's like going backwards when you're integrating instead of going forwards, but I think it's important to know, and it is another one of those useful mathematical identities of integration, much how remember we could split up an integral through a sum of integrals or a difference of integrals. You know, integrals are very, very similar to our limit laws. Turns out that we cannot conveniently multiply and divide integrals. That's actually very, very, very far down the line in calculus. That'd be like in the next calculus class. If this is kind of content in the first calculus class you would take, that'd be more so in the second calculus class you would take, right? And so I hope you enjoyed learning about bounded integrals and their techniques, what they mean, and how to compute them, their applications and all that. So anyways, see you later, class. Goodbye.